In this video, we are going to see a problem based on continuous time Fourier series. The problem is like this. We have to obtain Fourier series coefficients of the equation given, plus this time we have to plot magnitude and phase of Fourier series coefficients. The equation given is like this: x of t equals 1 plus sine omega 0 t plus 2 cos omega 0 t plus cos 2 omega 0 t plus pi by 4. So one simple thing over here is that all this we need to convert into a complex exponentials, and that we obtain by a Euler's identity, which says sine theta is nothing but e raised to j theta minus e raised to minus j theta upon j2, and cos theta is nothing but e raised to j theta plus e raised to minus j theta upon 2. So over here this will be a theta. For second term, once again same term will be a theta, but for the third term this entire thing is a theta. So let's find out now. So I can say that x of t equals 1 plus sine omega 0 t, I can write like e raised to j omega 0 t minus e raised to minus j omega 0 t upon j2 plus 2 times cos omega 0 t will be e raised to j omega 0 t plus e raised to minus j omega 0 t upon 2, and third and most important term, it will be e raised to j bracket 2 omega 0 t plus pi by 4 plus e raised to minus j 2 omega 0 t plus pi by 4 whole divided by 2. So what we have done, we simply use sine theta cos theta formula over here, so that all the sine and cosine converted into exponentials. Let's simplify it so that we can split it and we will club like terms. So let's split this. So x of t equals 1 plus e raised to j omega 0 t upon j2 minus e raised to minus j omega 0 t upon j2. From here I can cancel the 2. So the term left are plus e raised to j omega 0 t plus e raised to minus j omega 0 t plus 1 by 2 into e raised to j 2 omega 0 t into e raised to j pi by 4 in one bracket plus 1 by 2 bracket e raised to minus j 2 omega 0 t into e raised to minus j pi by 4. Now let's simplify this. So e raised to j pi by 4. So we know by De Morgan's theorem, e raised to j theta I can write like this: cos theta plus j sin theta. And this is true for plus and minus theta, just the imaginary part will get changed. So if I apply over here, what I will say, e raised to j pi by 4 is nothing but cos pi by 4 plus j sin pi by 4. Here minus is also there, so let's write it for both. Cos pi by 4 is 1 by root 2 and sin pi by 4 is also 1 by root 2. So in the end, what I can say over here, it is nothing but 1 by root 2 bracket 1 plus minus j. This is what e raised to plus and minus j pi by 4. So if I simplify and substitute over here, what I will get? X of t as 1 plus e raised to j omega 0 t upon j2 minus e raised to minus j omega 0 t upon j2 plus e raised to j omega 0 t plus e raised to minus j omega 0 t plus 1 by 2 in bracket e raised to j pi by 4 we obtained as 1 by root 2 plus j 1 by root 2 multiplied by e raised to j 2 omega 0 t plus 1 by 2 1 by root 2 minus j 1 by root 2 e raised to minus j 2 omega 0 t. What we can do? We can club the like terms. So I can club these two terms and these two terms, so that I will get x of t as 1. I am clubbing these two terms plus e raised to j omega 0 t is a constant. I can take it out. What I will get over here, 1 plus 1 by j2 into e raised to j omega 0 t. Over here I can take e raised to minus j omega 0 t common, and what I will get, 1 minus 1 by j2 e raised to minus j omega 0 t, and this will remain as it is. Just I will multiply 1 by 2 inside, so that I'll get 1 by 2 root 2 plus j 1 by 2 root 2 e raised to j 2 omega 0 t plus 1 by 2 root 2 minus j 1 by 2 root 2 e raised to minus j 2 omega 0 t. So now here we are getting a most important part of the problem, where all these terms, so in all 1 2 3 4 5 terms are there, and all the 5 terms are in terms of complex exponentials, which is nothing but a multiple of omega 0, where omega 0 is a fundamental frequency. meaning here the multiple of a fundamental frequency is 1. Over here it is minus 1. Here 2 is the number. So here 2 is the number which is getting multiplied with omega 0, whereas here it is minus 2. What about this? E raised to 0 is 1. So definitely a 0 is a multiple number for omega 0 over here. So if I see closely, I can say all the terms that we obtain over here, constants, are nothing but a Fourier series coefficients for that particular multiple. Meaning, I can very well say now A0 is 1. Now, as I said earlier, it's a multiple, a first multiple of omega 0, hence this will become A1. So A1 is 1 plus 1 by J2. Let's write it in a proper complex form, which will be 1 minus J 1 by 2. Next is this number, or we can take this number in a sequential manner that I obtain if I put k equal to minus 1. So obviously this will become a minus 1. So a minus 1 is 1 minus 1 by J2, which while writing in a proper complex form I will get 1 plus J 1 by 2. Next I have this, I obtain this when I put k equal to 2, so this become A2 1 by 2 root 2 plus J 1 by 2 root 2, and finally this I obtained if I put k equal to minus 2, so a minus 2 I will get 1 by 2 root 2 minus J 1 by 2 root 2. Some observation we can make out of it, and what is that? These two are complex conjugate pairs. Similarly, these two forming a complex conjugate pair. So I can say whenever I'm getting a Fourier series coefficient as a complex number, its conjugate has to occur, and that, if I see properly, will be just a symmetrical one. Means for a equal to 1, whatever we obtain, its conjugate will be there at a equal to minus 1. Similarly, a equal to 2, whatever we obtain, that will be a conjugate I will get at k equal to minus 2. So meaning every time we will get a magnitude plot as a even function that we will see just shortly. So what I have to do, these are the complex series coefficients we obtain. So just name it, or I can say it's a Fourier series coefficients. Now we have to get a magnitude and a phase plot. So let's find out its magnitude and phase. So let's start with k equal to 0, 1, 2, minus 1 and minus 2, because only these 5 terms we obtain. Then we will find out what is the AK, then mod AK and phase angle of AK. K equal to 0 is A0, and we obtain that as equal to 1. 1 magnitude will be 1, angle will be 0, quite simple. K equal to 1, we obtain this as 1 minus j 1 by 2. Just a complex number theory, I will get a magnitude as root of 1 square plus minus half square, which is nothing but root of 1 plus 1 by 4. Just a simplification which will give us answer as root 5 upon 2. Let's not concentrate on what is the root 5. So answer I am getting over here is root 5 by 2. Let's find out the angle. So angle will be what? It's a tan inverse imaginary part upon real part. So it's a tan inverse minus half, which is definitely minus tan inverse 1 by 2. Again, I am not interested in knowing what is the value over here, but it is some constant I will get, and most importantly it is minus tan inverse 1 by 2. Let's go for k equal to 2. So the AK we obtained as 1 by 2 root 2 plus j 1 by 2 root 2. So once again a complex theory, mod AK will be root of, so square of this, so let's do it directly. So square of this will be 1 by 8, square of this will also be 1 by 8, so in the end that will be root of 2 by 8. So if you solve this, we'll get root of 1 by 4, which is nothing but 1 by 2, and angle will be tan inverse of 1 upon 2 root 2 divided by 1 upon 2 root 2, so it's nothing but a tan inverse of 1. Since the value is already known to us, I can say it's a pi by 4. The most importantly, I am getting the angle over here as a positive angle, pi by 4. Now for minus 1, as we discussed, just a conjugate of this we will obtain, which is 1 plus j 1 by 2, whose answer straight away I can write now root 5 by 2, and angle will be minus tan inverse 1 by 2. The angle will be plus tan inverse 1 by 2 because all the terms are positive over here. And finally, for k equal to minus 2, 1 upon 2 root 2 minus j 1 upon 2 root 2, magnitude will be half and angle will be minus pi by 4. Now this particular table we obtain, we are interested in AK, mod AK and angle AK, which we call as a magnitude, and this we call as a phase. So magnitude plot of a Fourier series coefficient will be like this. We are having only 5 values: k equal to 0, k equal to 1, k equal to 2, k equal to minus 1 and k equal to minus 2. For remaining values it is 0. For k equal to 0 we obtain the magnitude as 1. For k equal to 1 and minus 1, the obtained magnitude is root 5 by 2. It's little more than the 1. For k equal to 2, it is half, and same will be the answer for k equal to -2. So this is a magnitude plot of a Fourier series coefficients. Let's plot phase angle. Once again, we are having a 5 values. For 3 onwards, it is 0 because no signal exists. For k equal to 0, the phase we have obtained is 0. For k equal to 1, we obtained a phase as minus tan inverse 1/2. So it will be like this. And for k equal to -1, we obtain the same value but with a positive sign. K equal to 2, we obtain pi/4. And for k equal to -2, we obtain minus pi/4. So it's quite obvious over here, in a Fourier series coefficient, magnitude plot is always a even symmetry, or you can say it's a even function. And phase plot is always a odd symmetry, or you can say always a odd function. So over here, what we have done, with the help of an equation given, we have calculated the Fourier series coefficients. We obtain complex numbers as a Fourier series coefficients. From that, we plot a magnitude and phase of those particular coefficients. Thank you.